Okay guys, in this video lesson we're going to introduce our next unit, which deals about energy and conserving it. It also deals with this idea that we're going to have energy changes that occur during a collision. Okay, so here we go. First thing we want to do is review kinetic energy. All right, so make sure we know the basic energies that we're going to be talking about in this unit. If you can recall, kinetic energy is solved by taking 1/2 the mass times the velocity squared, which means the faster that you move, the more energy you have, or the more massive you are, the more energy you have. Okay. Also recall that kinetic energy only exists when things are moving. Okay, so we got to make sure that keep that in the back of our heads. That's always about moving energy for kinetic energy. We also want to talk about gravitational potential energy. And we make a point to not just say potential energy, but we say gravitational potential energy. The reason for that is we are going to have another type of potential energy shortly. Okay, so recalling that potential energy for gravity is the height at which you place it, the mass that it has, and of course our acceleration due to gravity. Okay, so really this is all dependent on heights, or how high up you put it in terms of having it fall downwards. Okay. Now the new one we're going to add is elastic potential energy, okay, or energy that comes from deforming, stretching, compressing things, okay. So think elastomers, you think springs, think rubber bands, things like that you can actually create energy by pulling back on them and doing some work on them, okay. First thing we want to do is take a look at something called Hooke's law, because Hooke's law is our first step into understanding elastic potential energy, all right. What Hooke's law tells us is this: the force that a spring is applying will be equal to the opposite of a spring constant times the displacement which the spring is under. Okay, so we're focusing on the force that the spring applies, not the force that you apply onto the spring. Okay, so what I'm talking about is if I pull back on a rubber band, and that rubber band now stretches. Now I need to do some work on that rubber band and pull it back. So I'm putting a force into that rubber band. But at the same time, what's happening is that rubber band now is getting potential energy, and it is now has a force behind it. So if I let go, it's going to use that force to spring the rubber band forward and so forth. Okay, so let's take a look at what we're talking about here. So here's a typical spring, and right now I have no newtons of force applied to it, and I have a spring constant of 200 newtons per meter. Okay, so I'm going to turn on the applied force, the spring force, the displacement, the equilibrium position, and the values. I'm turning all this stuff on so we have tons of information to see. Okay, if I were to grab the spring and pull backwards on this, okay, notice that I have pulled backwards with 91 newtons of force. That matches my displacement. In return, the spring is now pulling opposite of me at 91 newtons of force also. So the harder I pull back on the spring, maximum of 100 newtons, is how much the spring pulls back on me. That goes back to our third law of motion, or of equal opposite action-reaction pairs for Newton's laws. Okay. Now, I got a 1/2 meter of pull out of this by doing this. Okay. If I put this thing back to normal and I change my spring constant, so let's say I make this thing much, much stronger. Okay, notice how what happens to our spring. We have a skinny little spring now, and I pull this over, and I now have a really thick spring. Okay, think of like a rubber band versus like those elastic bands that you might use when you work out in our weight room. Okay, we made the spring constant much bigger. Okay, so now it's going to take a lot more newtons per meter of pull. And now, if I pull, with 58 newtons, 100 newtons, I barely move this thing, okay? The forces are still equal to each other, but I'm barely moving it, right? Because I have such a high spring constant on my spring. As I lower my spring constant, we see that the spring will stretch more. As I raise my spring constant, it will stretch less, okay? So the spring constant is basically a measure of how strong the spring is, or how resistant it is to changing it, okay? Now keep in mind, I can also push, okay? So a lot of times we think about springs, I'll set this back to about 500, where we're always pulling them and stretching them. But at the same time, you can take a spring, and we call this our equilibrium position. So this is where nothing has happened. This is where it rests naturally, okay? The springs in your car, of your vehicle, when you hit a bump, they compress instead to absorb that shock, okay? So you also can compress that, where now we're pushing with 100 newtons of force inwards, so the spring pushes back at 100 newtons of force also, okay? All of this relationship is based off this idea of the force we put in comparison to that spring constant gives us our idea of the force that's available there or our displacement, okay? So it's a pretty linear relationship between force, displacement, and the spring constant. So that's what we're looking at. Now, if we go back to our equation, that would make sense because the force the spring generates would be equal to the spring constant and opposite of the motion. Okay, so let's review that one more time real quick. We go back here. The spring is in blue. It's pushing a force to the right. The displacement in this case was to the left. If I pull on the spring, the displacement is to the right. The spring provides a force to the left. So if it's right and left, they're opposites of each other. Well, if they're opposites of each other, we need a negative sign in our equation. Okay, so that's where Hooke's law kind of comes from. All right. Now, let's take a look at a little practice problem for Hooke's law. Okay, so originally a massless spring hangs vertically in a position of -3 centimeters from equilibrium. We give it a -3 because it's hanging downwards or being pulled down by that mass. The mass is 0.1 kilograms. Okay, you add another 0.2 kilograms to the spring. Let's see what happens. Okay, so first of all, how far will it hang from its equilibrium position now? Then how much upward force does the spring now exert? And finally, what is the spring constant of this spring? Okay. So let's diagram it out and then solve it, okay? So you do that first. Pause the video. When you're done, I'll show you how it works. Okay, go ahead. Okay, so here we go. We have a spring, and it's hanging down, and there's a mass attached to it that's 0.1 kilograms, okay? That distance it hangs down is a -3 centimeters. Then we take that spring and we hang a heavier mass to it. So we go from 0.1 and we add 0.2 kilograms. So now the spring hangs down and we have our 0.1 that was originally on it. And then we've added another 0.2 kilograms for a total of 0.3 kilograms, okay? Or basically, we now have 3 times of the weight on our springs, okay? So having that, if we have 3 times the weight, we should be able to predict pretty quickly what's going to happen to the stretch, right? The spring didn't change. The spring itself is the same. So if we triple the weight or we triple the force we apply to the spring, that means the spring is going to have to respond with triple the force back, which means that the distance is going to be triple too. Okay, so we go from 3 centimeters, so now it should fall down 9 centimeters. Okay, so that's our first part. Now, if we look at it mathematically, here's how you'd solve it mathematically. So we have force equaling -kx. Then we know the force is mass times gravity. So the mass times the acceleration due to gravity, is -kx. We had 0.1 to g and 3. We changed it to 0.3 kilograms. This now has to go to 9 because it's a relationship or it's a ratio between these two things. Okay, so it really isn't a solving. We don't know the spring constant yet. You could plug in these numbers here. That wouldn't do you any good. But we know that it's a relationship between those. So if we triple the mass, we have to triple the distance it travels because k stays the same here. Okay, so that's the first one. So now what's the upward force does the spring exert? Okay, and we have a force of our spring is the opposite of the force of gravity. Okay, so the spring opposes the movement, right? The movement was down, so the spring is pulling back up on it. So it's the opposite of your mass times your acceleration due to gravity. So it's the opposite of the 0.3 times the -9.1. So the spring is going to provide 2.94 newtons of force upwards. That's why it's a positive number here. So the spring is pulling back up, even though gravity or the weight is pulling it downwards. Okay. So now the question is, what's the spring constant? Well, we know the force on the spring, right? We know the x, so we know F and we know x. Well, if we know F and we know x, we plug it back into our equation and we solve for spring constant. So our force is this. We know it's -kx. We're solving for k, that's our spring constant. So now the force divided by the -x, so our force is 2.94 newtons. We had that from before. Our x is 9 centimeters or 0.09 meters. So it's the opposite of that, and it was a negative, so we end up with 32.7 newtons per meter is our spring constant. Okay. The spring constant here is kind of important because the stronger the spring, the more resistance it is to movement, the bigger that spring constant would be. Okay, so this one happened to be 32.7. If this was, 60 or 70, it would take a lot more force to move it further. Okay, so that's Hooke's law and how Hooke's law works. Now, Hooke's law leads us into this idea of what is elastic potential energy. Okay, and once we apply that, as you are creating a force, we know that there's a force over some sort of distance, right? If you have a force and you move in a distance, that's work, right? We learned that before. So now we're applying a force, we're creating a movement over distance of our spring, we're creating work. So we're doing work on our spring, which means we are now changing energy, right? Because any change in work or any work done is a change in energy. So it shouldn't be too big of a leap to realize that if we're going to stretch a spring, we need to put work into it. That work into it is going to generate what we call elastic potential energy. All right. So think about it. You pull back on a spring, it now has the potential to hurt you, right? No one likes it when someone points a rubber band at their face that they pull back. If it's not pulled back, you could care less. But you pull back on a rubber band and point at somebody, it's not very nice. But you do that, everybody cringes just a little bit because they're afraid that rubber band is going to be let go because it has the potential to hurt you, because by pulling it back, you did work on it. All right. So we actually can take the equation from Hooke's law, and it's actually an integral, but we won't get into that for you guys too much here. And from that, we can solve for the potential energy elastic now. Okay. That gives us 1/2 the spring constant times the displacement that you stretch it or compress it squared. Okay, that's our elastic potential energy here. All right. Again, our spring constant, same ones we used before. It's measured in newtons per meter. And x, again, is how far that's been stretched. So if we know these two values, the spring constant and how far to move it, we can solve for two things. We can solve for the force that is generated by the spring, and we can solve for that elastic potential energy that is there. Okay. Now, keep in mind, this is exactly the same if we talk about work, because the potential energy that we generate is from doing work on that spring. So the work the spring does is 1/2 kx squared too also. So if we ever need to worry about work, you can substitute work in for this just like we did in our last unit. Okay? So here's our practice problem now. A rubber strap is used to secure cargo. It is stretched 0.5 meters from its equilibrium position. It has a spring constant of 88 newtons per meter. What is the stored energy of the system? Okay, so we know the distance that we stretch it. We know the spring constant. Let's plug it in and solve. Okay, go ahead and do that and pause the video. And when you're done, we'll show you the answer. Okay, so here we go. We know our equation is potential energy elastic as 1/2 kx squared. We were given the K value. Our spring constant is 88 newtons per meter. We were given the stretch, 0.5 meters. We need to square that value. Okay, so 88 times 0.5 squared, take that divided by 2 or times 1/2, and we get 11.0 joules of energy here. Okay, so to do this stretch, we are giving that strap 11 joules of energy. Okay, it's not a lot, but it has 11 joules of energy there that is now potential. Okay, if that strap breaks, it's going to snap back. If you're standing next to it and it hits you, it's going to hurt because there was energy stored in that spring. Okay. We're going to stop here, guys. In our next video lesson, we're going to get into how we deal with all these energies together and conserving them. Thank you.